Okay, it's 7 o'clock, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? It's our last week of instruction, or last week of virtual instruction, I guess, right? It's been a long semester, I know, for more than one reason at all, for more than one reason, So, we're all at least for this, we're almost at the end. Right? All right, so hopefully everyone's doing okay, hanging in there. So a couple announcements before we begin today. So the plan for today is that I'm going to finish up just our last set of lecture notes, which is on turbulence modeling. So because of the situation and the move to the virtual instruction, I kind of had to cut the turbulence section pretty short. So we won't be able to do kind of a lot of useful things with turbulence modeling, even though I think it's something that's really important, especially if you're going to be working with turbulent flow. But we'll at least cover some of the basics. And at least some things, just some pointers for you to look out for if you're going to be working with mostly simulation technology, which is what a lot of people use to analyze turbulent flow. Okay? And then besides that, hopefully you guys got the email today. So I've posted a study guide for the final exam. So that's on Titanium right now. So if you look at that'll help you kind of guide your studying for the final. So our final exam is going to be next Wednesday. I believe that's May 13th. Yeah, next Wednesday, May 13th at 7 p.m. And then just like the first midterm, it's going to be a 24-hour exam. So you're going to have until 7 p.m. on Thursday, May 14th to submit it back. Okay? So take a look at the study guide. So it's if you look at the study guide, you'll see that it's a cumulative exam. So it's it covers stuff kind of from the very beginning of the class, but it's not totally cumulative. So I've gotten rid of some topics in the class, and I've gotten rid of some weeks worth of content, just because 15 weeks worth of stuff to study is kind of a lot. So I try to cut it down kind of as much as I can, basically to tell you, because I can't test you on everything on one exam. So I kind of limit it to the stuff that I can reasonably ask you on one exam. So please take a look and let me know if you have any questions on that. And then the other thing that's what the study guide is, so Wednesday we're going to have our final class session. So that's going to be a review session for the final. So just like we did for the first two midterms, if you look at the study guide and there's some topics where you don't feel that good about, or the learning objectives don't make that much sense to you, you can vote for those topics to appear. And then on Wednesday, I'm going to cover basically the top 2 or 3 topics that were on the poll. So please make sure you vote in that poll so that you get to see the topics that you want to see for the final review session. So the other announcement I want to make is on Wednesday, in the class session before this. So I actually teach a session before this. I'm going to be giving just a presentation on some of the previous work that I've done in my research life. So that's so that uses computational fluid dynamics to study blood flow. So if you're interested in tuning in, I posted the Zoom link on our announcements. So it's not the same Zoom link as our usual lecture. So it's the Zoom link for my previous lecture. So if you want to tune in and you're free during that time, definitely you're welcome to come. But it's by no means going to be required at all. So I'm not going to test you on anything on that. So that's only if you're kind of interested in seeing some of the research applications for a lot of the topics that we've been covering in this class. Okay. Okay. So besides that, the homework. So the homework is going to be due. So notice the homework has a different due date than normal. So instead of being due on Wednesday, I pushed it back a couple of days just to give you guys a little bit more time, and that's going to be due on Friday. Okay, so Friday at 11:59 p.m. So then basically after you guys turn it in on Saturday morning, I'm going to post the solutions so that you can have that to help you study for the final exam. Okay? So don't forget, homework 6 is due this Friday. Okay, are there any questions about the homework or just anything from the class that I can answer before we get started today? Okay. So if a question comes to you, definitely you feel free to either speak it out in the with your microphone or just type it out in the chat, and I'll answer anything that comes up. Okay. Okay, so our last topic for this semester is going to be turbulence modeling. Okay? So just to kind of recap from last week we kind of went over just an introduction to turbulence, so what it is and how people kind of generally think about it. Okay? So kind of the main features for turbulent flow that I kind of want to remind you before we get started today is first is that turbulent flow, when people think about it, they mostly think about flow structures of different sizes. Okay? Because normally when you have laminar flow, you have just a single length scale that kind of describes your entire flow. So if you think about flow in a pipe, your length scale would be the pipe diameter, and you could say that your flow structures kind of all have the same length scale. But turbulent flow is different from that. So turbulent flow, what tends to happen is you have these turbulent eddies that we talked about, so little pockets of vorticity, and those tend to break down into smaller eddies, and those tend to break down into even smaller ones. You have kind of, flow structures that have all different kinds of length scales. Right? Okay. And that description there doesn't really do it justice, because you can really have a huge variation in the amount of length scale. So I think, one example that we talked about is if you consider turbulent flow that happens either in the atmosphere or in the ocean, you can have some flow structures or some eddies that are on the size of kilometers long. You have these huge kind of eddies. But if the flow is turbulent, in addition to those flow structures that are kilometers long, you also have flow structures that are on the order of millimeters or sometimes even smaller than that. So you're going from kilometers down to millimeters. That's like 6 orders of magnitude that you're varying there. So it's really a huge variation. You have kind of pretty much everything in between there. And then what happens in turbulent flow is that these different flow structures, they all communicate with each other. So they pass energy to each other. And the way that they do that is the big flow structures, they tend to break up into smaller ones. So you have kind of this cascade of energy going from the large flow structures down to the smaller one. So we talked about that. So we called this the energy cascade. Okay. And so this continues to happen, or the kinetic energy basically continues to be passed from the large flow structures down to the small ones, until you get to the smallest length scale. So we call those the Kolmogorov length scales. And then once you kind of reach those length scales, then that kinetic energy gets dissipated due to viscous effects. Okay. So remember, we had kind of two different regimes. So we had kind of the breakup of big eddies into smaller ones. So that's purely an inertial effect. So there's no viscosity involved in that. And you also have the dissipation of energy at the smallest scales, and that was a viscous effect. Okay, so then the other kind of big idea that we went over is that turbulent flow, you can kind of break it up into two components. So you have kind of the mean flow. Okay. So the mean flow, that kind of describes kind of the flow that that governs kind of the bulk motion of your flow. Okay. And then the other thing that we went over was that turbulent flow can also be comprised of fluctuations. So those are kind of the random motions that people normally associate with turbulent flow. Okay? So these fluctuations are random. Okay. So in general, when we analyze turbulent flow, a lot of times what we're practically interested for engineering applications is most of the time we're interested in the mean flow. Okay. Because the mean flow is going to have all of your kind of your general mass flow rate and kind of bulk transfer of stuff that you associate with fluids. Okay, so the fluctuations are going to be there, but most times we don't really care about the fluctuation because if you actually do solve for them, it's just going to be a bunch of random shit. So then, for practical purposes, that random stuff is not that important. Okay, so what you're actually you know, to kind of summarize this, what you're really interested in is, like, you are interested in the fluctuations, but you're not interested in solving for them explicitly. What you really want to know is, how do those fluctuations affect the mean flow? Okay. And this is kind of the question that a lot of you know, engineers that work with turbulent flow, that's kind of the main thing that they want to do. Okay. So it sounds kind of a relatively simple question, but it's a question that has a lot of different answers. And actually, you know, the way that people kind of deal with this is kind of where the field is generally at right now. So lots of people are trying to think of different ways to model the turbulence, which is kind of the topic for this week. Okay. Okay. Any questions on this? Okay. Okay, so the other thing that we went over, which is kind of the way that, you know, the fluctuations enter the mean flow equation, is we went over this concept of the Reynolds stresses. So the Reynolds stresses is an additional term that enters into your Navier-Stokes, which captures the effect of the fluctuations on our momentum. Okay. Okay. And so once we plugged in this Reynolds stress or the fluctuations into our Navier-Stokes, we ended up with what's called the RANS equations. Remember, the RANS equation stands for Reynolds average Navier-Stokes equations. Okay. So just to remind you, let me write out the equation again. Okay. So I'm using the same notation as before. So basically, any quantity with an overbar over it, the overbar is going to denote an average. So the average denotes the mean flow. So that's what we're interested in. So first, we have the time derivative of our mean flow. Okay. So we have our unsteady term, we have our convective term. Then we have our pressure gradient, average. Okay. Then we have our viscous term, okay, averaged. Then we have this additional term at the end right here. Okay, so everything is basically standard Navier-Stokes. The only thing we have extra is this guy right here, where this is our Reynolds stresses. Okay. And so remember, when we talked about this, you know, even though this equation seems kind of succinct in that it doesn't add too much to our Navier-Stokes, it was actually literally impossible to solve. And the reason for that is because, you know, with conservation of mass and conservation of momentum, we only have 4 equations, which are usually enough to solve for the 3 components of velocity and pressure. But with the addition of this Reynolds stresses, we have more unknowns than we have equations. And so to actually solve this equation, what we need to do is we need to come up with a model for this Reynolds stresses. Okay? And remember, the fact that this equation had no solution, that was known as the closure problem of turbulence. So the idea with turbulence modeling is to come up with ways, either by adding additional equations based on some physical principles, to basically account for the effect of turbulence on the mean flow. Okay? So in this case, we're going to focus on methods that solve for the Reynolds stress or model that. But at the end of class today, I'll talk kind of very briefly about some methods that kind of take a different approach to turbulence modeling. But for now, we're going to just concentrate on just RANS-based methods that model the Reynolds stress. Okay. So we're just going to cover just kind of the basics of the basics. So mostly just the conceptual side. So, unfortunately, we won't do many practical calculations, but in reality, there aren't too many practical calculations people can do by hands, because most of these calculations are handled by computers, even with this RANS modeling that we'll talk about here. Okay. All right, any questions on this? Okay. Okay, so let's talk about what's known as Eddy viscosity theory. Okay. So the idea with Eddy viscosity theory is that we're going to take our Reynolds stresses, and since it kind of appears in the same place as the viscous stresses, what we're going to do is we're going to use a viscous model to model the Reynolds stresses. Okay. So the exact expression for that is given by the following. Right? So we're going to say that our Reynolds stress, which is given by u prime, outer product u prime. So remember the x with the circle around it, that's outer product. So this is going to be equal to two different terms. Okay, so first we have 2/3 k times I. So I right here is our identity matrix, and this k right here, this is our turbulent kinetic energy. Okay. So that term's actually not that important. We're going to cancel that out usually. And this is kind of the important term right here. Okay. So on the right here, we have nu T. So nu T right here, this is our Eddy viscosity. Okay. So you can think of it as or the way to kind of physically think about this is that it's an additional viscosity. So normally when you have a fluid and it has some viscosity, it has its kind of base viscosity. And then this eddy viscosity, we're going to just add on top of that. Okay. And then this guy, this is what you'll notice that this is the gradient of the mean velocity. So this is kind of a big kind of step right here. So it looks a little bit, innocuous, but let me highlight this word right here. So this is kind of the most important word here, because what we're doing is we're taking the turbulence quantities, which are usually random, and we usually don't really want to bother modeling them. And then through this Eddy viscosity theorem, we're going to basically relate those turbulence quantities, the fluctuations, to the mean field. And that's going to be huge, because it's going to simplify our equations kind of tremendously. Okay. Okay. So first, let me do this. Okay. Let me cross this guy out. So we're going to assume that this guy is 0, because we're going to assume our flow is fully developed. Okay. Okay. And so because we're assuming it's fully developed, because when we plug this into the RANS equations, we're going to end up with basically ddx of k, where k is our turbulent kinetic energy. So if our flow is fully developed, then we're assuming basically our kinetic energy is not changing with the flow direction. Okay. So that's mostly just to kind of simplify things just for now. Okay. Okay. So if we cross out that term, all we're left right here, this is basically going to be our turbulent shear stress. Okay. So then if we plug that back into our Rand's equations, we get the following. Okay, so we have our time derivative term as usual. So we have du dt. Okay. Okay. Then we have our convection term. Okay. Okay. Then we have our pressure term. So everything is the same as normal. Okay. Okay. Then once we get to the viscous term, you see that we have our normal viscous terms. We have nu times the Laplacian of the velocity. But then because we have this eddy viscosity, we're going to add that to our viscous term. Okay? So basically what this looks like is it looks like our usual Navier-Stokes equations, but we've augmented our viscous term. Okay. Okay. So this form is actually pretty nice, right? So because we've modeled the Reynolds stresses as a viscosity term, we've basically eliminated the turbulence from our equation. And then if we assume that this nu t is a constant, then we can solve it using the exact same methods as before, right? In theory. Okay? So before I kind of get to some of the caveats, are there any questions on any of this up to this point? Okay. So if we have that equation in that form, in theory, we can just solve it exactly as we did before, right? And so, some people would say, yes, it's just an additional viscosity, right? It's like you're just adding another constant to it, so that shouldn't be too bad. Okay. So the downside of this equation is that I haven't talked about how we actually obtain that nu t. So we've kind of talked about just the structure, the eddy viscosity, but actually obtaining values for what that eddy viscosity is, that's the really challenging part. Okay. So the key word here is accurate, right? And so because it's just additional viscosity, you can just plug in theory, you can plug in anything you want. So you can plug in 5, right? But that's not going to be accurate, right? And the thing that makes it really hard to guess is that it's not something that you can just measure in a lab. Because if you think about your normal viscosity, okay, our normal viscosity is it's a property of the fluid. Okay. Okay. And that's nice because if you think of just any fluid, you think of like water. So water is going to be the same if you're drinking it, from your glass as it is when it's raining outside, right? So you can take water and you can stick it in a lab and you can measure the viscosity because water is going to be the same as long as you still have the same kind of chemical composition. Water is going to be the same as before. So viscosity that you measure in the lab is going to be the same as the viscosity that you have in the sink. Granted, the same like temperature and stuff applies. What's difficult about the eddy viscosity is that it's not a function of the fluid, so it's not a property of the fluid, but instead it's a property of the flow. Okay. So it's going to depend on the specific geometry of your flow and the specific speed of your flow and the specific pressure of your flow. So that's not something that you can kind of take out of context and kind of measure by itself. So this eddy viscosity is going to be very different depending on your flow conditions and depending on the amount of turbulence that you have. So it's not something that's easily measurable. If it was, then it's, you know, I think a lot of people wouldn't have their jobs, but you know, that's what kind of makes it really tough. So there's additional equations that you can solve for this eddy viscosity, but there's also some kind of nice tricks or nice approximations that you can also do. Okay? So kind of the first approximation that I'll talk to you about is kind of known as a zero equation model, in that you don't have to solve any equations. But from the zero equation model, you basically work from dimensional considerations. Okay. So when I mean dimensional considerations, I talk about, you know, let's look at the dimensions and let's look at the units of viscosity. Okay. So even though the mechanism is pretty different, the eddy viscosity still has the same units as normal viscosity. Okay? So the SI units for normal viscosity are meters squared over second. Okay. So one way that you can obtain this is that you take some length and you multiply by some velocity. Okay. So I put an underscore T right there to kind of denote turbulent. Okay. So if you can take your flow and you can kind of come up with some, you know, length scale that kind of characterizes the turbulence, and you multiply it with some velocity scale that kind of characterizes the turbulence, maybe the actual fluctuation velocities, then that will give you some estimate for nu T. Okay. And so one theory that we can use for this is we can call this LT, we'll call this a mixing length. Okay. And then this UT, this is a turbulent velocity scale, which we can determine from the mixing length. Okay. Okay, so then the next topic is going to be the mixing length model, which is kind of a way to kind of estimate this guy. Okay. All right, any questions on this? Okay. Okay, so let's go over mixing length model. Okay. So the LT in the previous page, remember that's a mixing length. So there's kind of lots of different ways that you can interpret that. So one you know, way that people have interpreted it is as a mixing length. So what that means that this is the kind of the approximate length that a fluid particle will travel in the cross stream direction before it kind of loses memory of where it was before. Okay. So this is the distance a fluid particle will travel before losing its previous momentum. Okay. Because we talked about before in turbulent flow, you can have fluid particles that kind of jump different layers because you have kind of this random motion. Okay? So if we think about just a kind of a physical example here, so say that we have a boundary layer, turbulent boundary layer, and then let's say the velocity profile looks like that. Okay. And so if we have a particle, a turbulent particle, remember the particle can have kind of any random motion, and it kind of jumps from this bottom layer near the plate up to this top layer, okay? It kind of moves that distance before it kind of becomes brainwashed by that fluid layer, okay? Because remember what we talked about last time is that when fluid particles jump layers like this, it carries some of this momentum information. So it goes from a region with kind of relatively low momentum near the wall, and it goes to an area of higher momentum kind of away from the wall. So if it can travel that distance kind of before kind of, losing memory of where it came from, this right here would be the mixing length, okay? Right? And so if we have this mix, if we kind of define the mixing length in this way, we can also define the turbulent velocity in kind of the same in terms of this. Okay. So the turbulent velocity, you can kind of think of it as the change in momentum that occurs as the fluid particle jumps that distance. Okay. So you can say that UT is going to be proportional to LT, which is the distance that it traveled, multiplied by the gradient of velocity. Okay. And remember, and you can see here I put a bar over it, so that's the gradient of the mean velocity. Okay. So in the one-dimensional case, we can say that this is equal to LT times partial U bar partial Y. Okay. Okay. And then once we do that, we can plug that in, and we can basically have an expression for the Reynolds stresses. Okay. All right. Any questions on this? Okay. Okay, so if we plug that in for our Reynolds stresses, we get the following. So our Reynolds stress, remember, was this. So with the Eddy viscosity theory, we say that this is equal to nu T. And then let's take the one-dimensional case. We have du dy. Okay. So this is like our turbulent viscous stress. So we have our turbulent viscosity multiplied by the mean velocity gradient. Okay. So if we plug in our mixing length model, we know that nu T is going to be equal to LT times UT, okay, times du dy. Okay. And then if we plug in for our expression for UT from the last page, then we get LT squared du dy squared. Okay. So now we have an expression for the Reynolds stresses where we have only one unknown, and that unknown is LT. So now we need to plug in something for the mixing length. Okay. So this is kind of unfortunately where you know, a lot of people get stuck on, because, you know, if we kind of go based off the definition here of this, this distance that fluid traveled, right? You know, obviously this is going to depend a lot on the flow. And it's not something that's kind of easily estimatable. But we can come up with some cases where you can come up with an estimate, okay? So if we take kind of the case of wall-bounded turbulent flow, which is kind of the last thing that we covered last week, we can come up with a reasonable expression for LT. Okay. So for wall-bounded turbulent flow, we can say that LT is going to be approximately equal to K times Y. Okay? So this K right here is just some constant. Okay? So it's not the turbulent kinetic energy, so it's just, you know, another constant. And Y right here, that's the distance from the wall, so that's physical coordinate Y. Okay. Okay. So if we plug that in, okay? So if we plug this expression into our Rand's equations, and we assume steady and fully developed flow, we'll assume 1d2, so basically we can cancel out the entire kind of left side of the equation. We get the following expression. So we get 0 you get 0 is equal to minus 1 over rho okay, minus 1 over rho dp dx plus nu d squared u bar dy squared, okay, plus d dy of d dy of k squared y squared du dy squared, all in parentheses. Okay. So here we have our pressure term, we have our normal viscosity term, and then we have our eddy viscosity term, where for the eddy viscosity term, we plugged in our mixing length model for the turbulent velocity, okay? Or turbulent viscosity, sorry. Okay. So obviously, you know, you can see here that it's this is a partial, or it's an ordinary differential equation, believe it or not, for the velocity, but it's extremely nonlinear, because you not only do you have a y squared here, but you also have a the derivative of our quantity raised to the second power. Okay? So this is only going to be an equation that you can solve under very heavy assumptions, which we'll do in the next slide. Okay? Before I do that, are there any questions on this? Okay. Okay. So on this equation, let's apply some more assumptions. So first of all, let's assume that the pressure gradient is negligible. Okay. So we can basically cancel out the pressure term. So if we do that, we get 0 is equal to nu d squared u bar dy squared, okay, plus d dy of k squared y squared du bar dy squared. Okay. So we can integrate this in y, right? So then if we integrate this first in y, because you can see every term has at least one derivative in y, okay? We get 0 is equal to, or c, because we integrate the left-hand side, we get some constant c is equal to nu du dy plus k squared y squared du bar dy squared, okay? And then we know that this is going to be equal to the wall shear stress divided by rho, okay? Because we kind of evaluate this at y is equal to 0, then we basically just get kind of the balance of forces, which gives us the wall shear stress. Okay. So this is a little bit better. So we're getting close to something that we can solve, but our equation's still pretty nonlinear. So let's assume one more thing. Okay. So if you remember when we did a wall-bounded turbulent flow, we went over kind of all the different layers that can appear in our equation or in our situation. So remember we went over 3 different layers. So if we assume that we're kind of outside the viscous sublayer, so if we assume we're outside the viscous sublayer, we know that the viscous stresses are going to be negligible. Okay, so if we do that, we can cancel out that term, and we're left with just a simple equation. Okay, so we're left with tau naught over rho is equal to k squared y squared du bar dy squared. Okay. So this, even though it's a nonlinear differential equation, we only have just one derivative left. So we can actually divide, take the square root, and then integrate. Okay. So if we do that, you get du dy is equal to 1 over ky square root of tau naught all over rho. Okay. And this gives us, after you integrate and solve, you get u bar over u star is equal to 1 over kappa, or 1 over k, ln of y, okay, plus some const. Okay. Right. And so if you remember, at least you remember this kind of logarithm here, you can see that this is the same as our law of the wall. Okay. So you can see that at least for this kind of very kind of contrived case of wall-bounded turbulent flow, this Eddy viscosity model with the mixing length at least comes up with something that's at least been observed experimentally. Okay. All right. Any questions on this? Right. So the question is, what does the C represent again? So this C right here, that's just some constant that you get from integrating. So how we got from the first equation to the second one is we just simply integrated this entire equation in y, and then we basically by integrating that 0 we get a constant. Yeah. Yeah. So but for this case, we actually know what that constant is, or we can actually solve for it. So we can basically apply this this whole equation here. If we apply that at y is equal to 0, then essentially what we're getting is just the stress at the wall. And so since the wall shear stress is a parameter that we can that we know, that's what we're basically plugging in here. So we say that this constant, what it has to be is it has to equal to the wall shear stress divided by the density. Right? Any more questions on this? Yeah. Yeah, so that's basically an assumption that we're making. So this form of the equation is not that, it's not super useful, as we'll kind of go over now, but this is just kind of a very contrived example to kind of show that, you know, this mixing length model is actually consistent with something that we've covered before. in practice, no one uses the mixing length model, but it's kind of a nice stepping stone towards some other stuff. I think it's more useful conceptually more than anything. Yep. Okay. So as I just mentioned, this mixing length model, it's known as what's called an algebraic or a zero equation model. Okay. Okay. So it's known as a zero equation model because we didn't solve any additional differential equations. So we basically just assumed just an algebraic expression, just basically purely based off dimensional considerations for the turbulent viscosity. Okay? Because remember, what we're looking for in this case is some expression for nu t. Okay? And so the mixing length model is just a very simple algebraic expression for nu t based purely on dimensional considerations. Okay? So in practice, this zero equation model, even though it's something that you can reasonably do by hand under very contrived situations, it's not really useful in practice because it's there are more complicated models and a lot more accurate models that exist, but a lot of times you can just have a computer solve them. Okay? But with that said, this mixing length model still has some practical use. Because what it can be useful for is kind of what's known as a back of the envelope calculations. Okay. Okay. And so that's a term that you might hear quite often. So if you've never heard it before, all that means is that it's a way to basically quickly compute something for a very complicated engineering situation. So in this case, turbulent flow, a lot of times people solve it with very powerful computers, but you don't have a powerful computer on demand all the time. But sometimes you just kind of want to get just a guesstimate or just an educated guess for kind of some of the turbulent effects. And a zero equation model like a mixing length can be useful for that. So it's, the way it gets this term is that before what a lot of people did was they took literally the back of an envelope and they just scribbled some very quick computations. And then from there, they were able to at least make some reasonable engineering judgments. They wouldn't have the exact numbers because they would have to run the full calculation, but it would at least be something to get a conversation going. Right? So that's what the mixing length models can be good for. Okay, so it can be good for kind of to give you a kind of a general idea or a general sense for how big the turbulent effects are without actually performing an expensive simulation. Okay. Okay, so let's do kind of an example to kind of show this. So let's say that we have a turbulent flow in a pipe. Okay. Okay, so here's my pipe. We have the lateral walls. Okay. Right, and there's my velocity profile. So if we solve this problem in the laminar sense, you would expect a parabolic profile that looks like that. Okay. But since we have a turbulent flow, we know that our velocity profile is going to deviate from this laminar case. Okay. And so what we want to do is we want to use the mixing length model. Okay. And we want to use the mixing length model to estimate in parentheses, I'll say, I'll put roughly. So we want to roughly estimate the turbulent velocity profile. Okay. And so the way that we're going to do this, we're going to estimate a value for LT, which is the mixing length, and we're going to estimate a value for UT, which is the turbulent kind of change in velocity. Okay. Okay. Let's see. Okay, so we're going to do. Okay. And so once we have LT and UT, we can basically just multiply them together, and then that's going to be our eddy viscosity, and then we'll use that to modify our laminar velocity profile. Okay. All right. Any questions on this? Okay. So for this problem, it's going to be a lot of kind of and even I'll admit this, some kind of dubious reasoning, but I just kind of want to just give you kind of a sense for what these kind of values mean and how you can actually compute them. Okay. Okay. So let's start with LT. Let's start with the mixing length. So remember, the way that we define mixing length is this is the distance that a particle can travel in your turbulent flow cross stream direction before it loses its momentum, or it loses its kind of memory of where it was. Okay? So in reality, this is something that's really, really difficult to estimate for kind of a general turbulent flow. But in this case, since our flow is basically confined within the pipe, we kind of know what the upper bound of this is. Okay? So we can say that LT, the mixing length, is going to be at most the radius of the pipe. Okay? And I didn't write it on the previous one, but we'll say that the radius of the pipe is capital R. Okay? Capital R for Team Rocket. Okay. So UT, remember UT, we define that as kind of the maximum change in velocity that a particle can see. Okay. So since we have kind of the no slip condition at the wall, the maximum change in velocity kind of occurs if you go from a turbulent, if a particle goes from kind of the middle of the pipe up to a wall, we say that the maximum change in velocity that can occur is basically going to be equal to the maximum velocity. And so what we're going to do is we're going to solve the laminar problem first. We're going to evaluate that laminar velocity profile at the center, get that U max, and then multiply it by big R, which is our LT. Okay. Okay. So let's solve the laminar problem first. So we know so if you solve the cylindrical Navier-Stokes, you get the following equation. So you get U lam as a function of R is equal to 1/4 nu dP dz, which is the pressure gradient down the pipe, little r squared minus big R squared. So this velocity profile is going to serve two purposes for us. So we're going to use it first to evaluate UT. Okay? And then once we evaluate UT, we can plug that back into this expression after we solve for the eddy viscosity to get the turbulent velocity profile. Okay? So first, let's find the max. So U max is just going to be U lam at 0. Okay. So U lam at 0 is going to be minus 1/4 nu, okay, dp dx, or z, sorry. Okay. Big R squared. So usually we take the magnitude of this, we'll just add a plus right there. Okay. And so therefore, so this is going to be our UT. Okay. So therefore, now that we have UT, and we say that LT is just equal to big R, we have an expression for LT, or a new T, sorry. So our turbulent eddy viscosity is going to be LT UT. So in this case, it's going to be 1/4 mu, sorry, dp dz r squared. Okay. And then to convert this to dynamic viscosity, okay, just so it'll be kind of easier to plug into our laminar velocity profile on the previous up here. Okay. We're just going to multiply this by rho. So if we do that, we get 1/4 nu dp dz r cubed. Okay. So basically, I just multiply this upper expression by rho. So then here you have rho over mu. So rho over mu is going to be equal to 1/nu, which is the kinematic viscosity. Okay, any questions on this? I don't recruit for Team Rocket, but it might be a second job for me if you know, if lots of bad stuff happens. Okay, so let's go ahead and plug that in. So basically what we're going to say is now that we have our turbulent viscosity, we can say that our total viscosity is going to be the sum of our regular viscosity plus our turbulent one. Okay? And so if we plug that in, we get our U turbulent. Okay? It's going to be equal to 1/4. And this is equal to mu plus 1/4 nu dp dz r cubed, okay, times dp dz little r squared minus big R squared. So you can see our turbulent velocity profile basically has kind of an additional terms on the bottom there. So if you kind of plot this and you plot this against our laminar velocity profile, what you'll see is that the turbulent velocity profile looks a bit more blunt, and that's kind of the term that people use. Okay? So let me draw this out. So I'll say that, you know, this velocity expression that we got up here for this turbulent one, that's under a lot of very heavy assumptions. So it's not really like this in reality. But what I kind of wanted to illustrate with this was that, you know, through this, your viscosity will become significantly enhanced through the effects of turbulence. And so if you actually, you know, look at this in practice, I kind of need to be really careful when drawing this. So what I've drawn right here first, this is kind of our normal laminar profile. So you can see our laminar profile has a very kind of parabolic shape. But if you compare this to the turbulent one, what tends to happen is that you have something that looks like this. Okay? So you'll have something that it kind of has two features. So the first feature, let me label this first. This is U-turb, okay, so we're U-turbulent. The first feature that you'll notice is that it doesn't come out nearly as far as U-laminar, so the maximum velocity for the turbulent flow is going to be much less. Okay. But to compensate for this, what you have here are these kind of regions right here, okay, which I'm kind of shading in. Actually, I can do a different color here. Okay. So in those regions right there, what you'll see is that the turbulent profile kind of has a much sharper gradient near the walls. Okay. And these are kind of both the result of kind of that enhanced momentum mixing that we talked about before. You know, that turbulent flow is known for. So because you have that enhanced momentum mixing, you have sharper gradients near the walls, but then you have much a lower kind of maximum velocity. So what ends up happening is that this looks very blunt. Okay. So instead of kind of a nice kind of sharp kind of profile with kind of a nice point at the end for the laminar one, you have one that's kind of like a dull blade, so something that's like that. Okay. And then also another thing to note is that if you actually kind of plugged in numbers for this guy, what you'll usually see in most cases is that the turbulent viscosity, ut, is going to be much higher than the regular viscosity. Okay. So turbulence is going to be a much more effective means to mix your viscosity than it is the normal. I mean, the turbulent viscosity would be a much better way to mix your momentum rather than the normal viscosity. So, you know, that's kind of consistent with kind of everything that we've heard before, where for turbulent flow, you kind of ignore, and the Reynolds number is really high, you ignore the viscous effects because these turbulence and these inertial effects tend to dominate a lot more. All right, any questions on this? So the R cubed came from kind of the product of these two right here. Okay. So we found that the UT had this R squared right here. Okay. So we assumed that UT was going to be the maximum velocity in our pipe. So we basically plugged in 0 for little r, and we get this R squared. And then to get the new t, we multiplied it by LT. And here we assume that LT was a big R. So we have, oh, there should be a 3 here, sorry. So therefore, the turbulent viscosity or the eddy viscosity is going to be r squared that comes from the velocity, and then an additional r that comes from the L. So you get r cubed, basically. Yeah. All right. Any other questions on this example? Okay. So now let's now what I wanted to do is I kind of wanted to just go over some just talk in general about some of the other more common turbulence models. So we went over mixing length model, which is kind of good for back of the envelope calculations, but it's not really used for anything practical. So now let's talk about kind of a different way to estimate the turbulent viscosity, and that's what's known as a two-equation model. So this is used quite often in practice, actually. So this is kind of a more accurate way, or a better way, to estimate our eddy viscosity. Okay. And so with the two-equation model, the first one that we'll go over is known as the K epsilon model. So it's called the K epsilon model because you know what you're going to be solving for in the two-equation model is you're going to solve one differential equation for K, which is our turbulent kinetic energy. Okay. So our turbulent kinetic energy is TKE. Okay. And then epsilon, if you kind of remember this from last week, this is what's known as our viscous dissipation rate. So basically, it's the rate at which energy is converted to heat at the smallest length scales in our turbulent flow. And so under those two parameters, our nu T is equal to a constant. So this constant right here is C mu, okay, C sub mu, times K squared divided by epsilon. So this right here is a model constant. And believe it or not, this is something that you have freedom to choose. So depending on your flow, you can choose different values for K for C mu. Okay. And then in addition to this, you have two partial differential equations, which are fairly nasty to solve for K and for epsilon. Okay. So let's do the first equation, which I might be able to fit. So first we have dk, or partial k, partial t, plus the convection of k. Okay. So the left-hand side is nothing more than just the material derivative of k. Okay. Okay, then you have nu t divided by sigma epsilon, where sigma epsilon is another constant, okay, times the gradient of k minus epsilon minus your Reynolds stress, dotted with the gradient. So this sigma right here is another constant. So you can see basically we have kind of a mini Navier-Stokes here. So you have kind of another partial differential equation to solve. So, obviously this is not something you want to solve by hand. This is something that you would solve in the computer, especially with like all the constants and kind of all the coupled equations going around. So even though this equation is for K, you can see that we have epsilon that shows up here too. So it's, these two equations depend on each other. So you really kind of have to rely on computers to solve this. So that's the first equation. So are there any questions on this before I list the second one? Okay. So we're running a bit short on time, so I kind of want to get to the end. So let me write out the other one. Okay, so this is the other equation for epsilon. So you can see it's another extremely complicated equation with some more model constants in it. So basically, whenever you see a sigma or a c, those are basically constants that you can specify. And so some standard values for this are given by the following. So our first model constant was c mu. So that was in the kind of the first algebraic equation that we saw. So the standard value is 0.09. So these are some of the standard values of these. So actually, if you use this this K epsilon model in a CFD code, these might be kind of the default coefficients. But you can modify these based on the flow. So unfortunately, I don't have the experience to really know, how you would change these or why you would change these. But I know that these are kind of some parameters that you can actually set in your CFD code. But how or why you would change this, I don't really have the experience to say. So I don't really want to comment any further on that. Okay. So that's, we've up to this point, we've covered kind of one general broad class of turbulence models. So those are, all of these are kind of belong to the family of what's called eddy viscosity models. So they're kind of ways to estimate this eddy viscosity. And we use these to plug into our RANS equations. Okay? So believe it or not, that's just kind of one small class of turbulence models in kind of the grand scheme of things. So what I want to do kind of for the last 5 minutes is just kind of talk about some other turbulence models that I've heard about in practice and kind of the pros and cons of each one. Okay. So if you're going to work with turbulent flow, especially simulations, these are terms that you'll definitely come across. So the first one I want to go over is a direct numerical simulation. Okay. Otherwise known as DNS. Okay. So this type of method here doesn't make any assumptions. It doesn't it doesn't have any kind of cutesy model for the turbulence effects, because you can kind of think of DNS as kind of like a raw brute force way to model turbulence. So DNS doesn't do anything special, so it just solves the normal Navier-Stokes. How it gets its theme is that you use a grid, or you use length scales that are so tiny that you can capture all of the different length scales in turbulence. Okay. So DNS is kind of like the gold standard, because you don't really make any assumptions, you don't make any kind of cutesy modeling, you just kind of brute force the heck out of it. So unfortunately, with all brute force methods, this is even though it's really accurate, it's also extremely expensive. So if you're going to do a DNS, you can expect to run a simulation on maybe hundreds of thousands or even 1 million processors, and it's going to be running for like 2 weeks, 3 weeks, even like over a month. So you really got to know what you're doing if you're going to be using this, because you're going to be taking up a lot of resources. So that as you can imagine, DNS is used by the military because they kind of have the budget to do it. But for a lot of research labs, this is kind of outside our usual budget. But it's good to know what it is, and it's good to be aware of the people who have done DNS, so you can kind of compare your results against those. Okay. So the next class is known as large eddy simulation. So this is known as LES. Okay. So it, just as kind of the name indicates, large eddy simulations, you're only going to simulate just the large flow structures. And then what you're going to do is that you're going to account for all the small flow structures, but you're kind of account for them in kind of an indirect way. So LES, it's a very popular method because in terms of cost, it's a lot more reasonable than the DNS, or direct numerical simulation. And for a lot of situations, it kind of gets you kind of the primary effects, which is what you want. So LES is popular. So it's kind of similar in concept as eddy viscosity in that you're kind of producing a model for the small scales. It goes about, it's just the mathematics behind it are a little bit different. And then the last one that I want to go over is kind of the one that we've been discussing so far, known as RANS. Okay. So RANS stands for Reynolds Average Navier-Stokes. So that's the one we've been going over. Okay. So RANS is also a very popular method. So I know a lot of people use RANS simulations. Okay. So the only catch with RANS simulations is that you also have to choose a model for the turbulent, for the Reynolds stresses. So an example of one such model is the one that we just talked about, which is the K-epsilon model. Okay. And the K-epsilon model is just kind of one example, but there are a lot of other models out there that you could choose for a RANS simulation. But kind of the ones that kind of are kind of the workhorses, you call them the workhorses for turbulent flow simulation. I think a lot of people use RANS. So RANS is kind of known as the one that a lot of people use. LES kind of comprises kind of a decent portion, but not nearly as much as RANS. And then for the small select few, the lucky few that get access to tons of computing, they can run DNS. Right? All right, so any questions on any of this? All right, so I ran over time a little bit today, so I apologize for that. But that's all I got on turbulence modeling. So I had to cut it a bit short because of the situation. Because normally I'd like to kind of go over all these different kind of models, but that's kind of all we got planned for this semester. So that's it for the content of the class. But we have one more class session, and remember that's going to be our review session. So please vote in the poll for the topics that you'd like to see, and on Wednesday we'll review for the final. So have a good night, everybody. Please stay safe. Please stay healthy, and I'll see you guys on Wednesday. All right, thanks, everybody.